And yes, hi everyone. Let me hold on a second. No, this is not quite ready. Hold on, slideshow. Current, no, current. Oh, yes. Okay, now. Sorry about this. Okay. All right. By the way, I posted links to these slides on the chat. Okay. So chosen ciphertext attacks. So for the first time, we encountering active attacks. Let's jump to it. So the chosen plaintext attack security was basically capturing the following attack. You had intuitively you had some encryption box out there. You can think of it as a sender in the encryption scenario, and adversary got to see ciphertext that this sender sends out, let's say to some receiver, right? And it is the adversary who chooses which messages the encryptor will send. The goal of the adversary is to determine which of the two traffic patterns the encryption encrypted. So was this box outputting CIs consistently as encryptions of MI0, where this bit is B0, or MI1? So he's always encrypt the left or right side of the pair. But basically what this models is an eavesdropper. Even though it's an eavesdropper that chooses the application, if you will, and the message space, and basically what these messages are, but his access to encryption is just he sees ciphertexts. He doesn't try to interject anything between these two communicating parties. And what would it mean that an active attacker who sits in between? So what does this model can? There is some server, there is some sender and receiver, things like a website and a client, establishing as TLS, establishing a shared key K, and using it to communicate the traffic by encrypting it. Adversary gets to see all these ciphertexts. These are these. What does it mean that he actively participates is? Well, he could send also some ciphertext to the decryption box to the receiver and observe what does the receiver do with the result, right? Because what does this box do? It takes whatever inputs it receives on this wire and interprets this as a ciphertext and decrypts it. Now, it's a little maybe funny to assume that the result of this description is that, excuse me, it's just going to be given back to the adversary. And yet, what it really happens with decrypted plaintext, right, is that they're fed into some application. And based on this plaintext, some upper layer application is going to perform some function, right? So either if the upper layer likes this message in some way, it's going to do one thing. And if it doesn't like it, it's going to do another thing. And this is not just binary choice, right? Like there is basically many forks that the upper layer computation can take depending on this decrypted plaintext. And who knows what this application really does? Perhaps it partitions the decrypted plaintext into some bunch of boxes, and its actions on those inputs are externally observable. And therefore, what the attacker gets by just simply observing, does this box output a message at all back? Is it big? Is it two messages or just one? Right? Attacker who sees this, the wire, who is an eavesdropper on that wire, he will see these responses. And he will make some conclusions about what this message was. So without a loss of generality, there is no hope that we can say encryption is secure no matter what application does with these messages, unless we simply say, let's surrender the decryption message and just assume that the application on top does the worst thing possible, which is to output it. And don't just give some information function, like, is this message the kind I like or the kind I don't like, which is a single bit computed on this message. Just simply give this message back. Okay. And of course, the adversary can recurse, right? He observed what this receiver did with the decrypted plaintext, so now he can modify another ciphertext and observe what happens in response, right? This is called chosen ciphertext attack, right? Because though sort of clear from the picture, on the left-hand side, adversary chooses plaintext on which it sees result of encryption. On the right-hand side, it chooses ciphertext and it sees the result of decryption. Here is an example of where this could happen. So like think TCP IP, there is a client and a server, and there is a packet transferred. And based on the decrypted, so inside of the packet, there is a destination IP address of, within the LAN here, with the IP address of the real receiver. And now let's say, so if this is a CPA secure encryption, this is like a box. Adversary doesn't know anything about the inside, right? He cannot distinguish an encryption of proper data with an encryption of some constants. So he cannot tell anything about this insides. But let's say that, so that's a passive attacker who just observes this. Let's say it's wireless. So by default, you leak these and send messages, right? The ciphertexts that are on the wireless wire. Okay, but let's say that if attacker could change the data inside, so that, let's say that this is a UCI, and there is some entity on the inside with some other IP address, or this is like in this application, these are processes on the same machine. So let's say one is a viral process, which is registered listening at port 25. If attacker could modify the ciphertext to create a new one, which basically preserves the data, but replaces port 80, which is, let's say, a standard www, which it is port, with port 25 of this malicious process. Then what this guy does is that he decrypts this, sees the port, and takes the packet and forwards it to the proper port. Okay. And if you think, if it is the same stuff, it's like when this is a router and all of this inside are just different IP addresses, where you can be like, well, if I have one malicious process on a platform, then perhaps I should give up on security entirely of all the other processes. Well, you definitely cannot give up on the security of the whole LAN just because on one of the IP addresses sits someone who is spying on you and you don't like this person, who's trying, basically you're an enemy. So here is that you can do this transformation if you use counter mode encryption. So this was our first CPA secure encryption, and in fact, we've seen just a couple, right? CPA counter mode, CBC mode, and OFB in the homework. Okay. The same is going to hold for stream cipher, even easier to see. So, but look at counter mode. So the ciphertext in the counter mode is a counter, the first part of the ciphertext, and the second is a PRF with this key applied, so block cipher to the counter, and then the result is XORed with the plain text, right? So if the plain text is all this stuff, let's say, just assume that it's a single block, okay? Nothing changes if there is more, if you parse this into a bunch of blocks, nothing fundamentally will change in this example. So just assume it's a single block. So what do you do? Take a delta, which is a bit string that has all zeros. In the number of these zeros is the same as the length of the counter, so a block size. And for the rest, let's say this is a single block, and let's say because this is a standard formatting, that exactly where the port description is within this packet. And you take the 25 rendered as a byte, probably, right? And you XORed that byte with the bytes that represent 80. And then it's all zeros because you want to preserve the rest of the data. And what you do, the ciphertext, the new ciphertext, the modified ciphertext, is the original one XORed this delta shift. And what did it do? So the bytes representing the ciphertext are these. When you XOR them with these bytes, the counter X got XORed with all zeros. So the new ciphertext is still the same, has the same counter. The FK of counter XOR M got XORed with this. But whatever this is, therefore is incorporated basically into this message, right? Because you're XORing three strings, FK of counter, M, and this part of the delta. So that's the same as taking FK counter and XORing it with an XOR between message and this stuff. So that's your new message prime. It's a message XORed with this shift. And the shift was hacked so that at the position of the port, you took a byte 25, XORed with the byte 80. M contains byte 80 at this position. So when you XOR it, what gets implanted here is in M prime is the port 25. And the data is carried because this part of the delta shift was all zeros. Okay, so maybe I'm belaboring this, but you can see that this way created a valid encryption of counter mode encryption of a message which is closely related to the one encrypted here. Closely related in very predictable and beneficial to the adversary way. Namely, data is copied, and the destination is just switched from a known 80 port of the World Wide Web to the port of this malicious process. Okay, and nothing changes if these are IP packets and these are IP addresses. If you know the IP address of the destination, which you usually do, then you can just XOR out that part of the ciphertext with the your desired IP address, and the decryption would get that. The decryptor would get this new IP address in the place. And usually, by the way, if you don't know something, but there is a range of possibilities, you try each one and see if they work, and you observe the system, because normally in any communication system like TCP/IP, you can tell from acce and nax that come back whether or not this guy was happy with the result, right? So if you ended up XORing something that didn't even parse like a proper IP address, you will know by the type of error messages that coming back. So you just recurse this until you hit. If the space of IP addresses is predictable, again, these spaces are often predictable. Here's another example. So let's say that the application is a terminal app. So the client server, and this is okay. It's I forgot. It's SSH, I guess. So this guy with the key, he encrypts. And the thing is that because it's a terminal, so he encrypts very small messages, keystrokes. Every time he types, that generates an encryption of an IP packet that contains an encryption of this keystroke gets decrypted here, right? And so on and so forth, right? So now in a terminal app, so what is in the packet? So this is a TCP connection. So it's some TCP header stuff, but you know, that gets encapsulated right into an IP packet. So there's an IP header. And what's the real payload? There is a tiny payload, 1 byte of a keystroke, and a checksum, 16-bit checksum. Okay, that's the app, and that is encrypted. Now imagine that this is encrypted using just CPA secure encryption, like counter mode. So the same attack like before, if you XOR this with the appropriately chosen shift, which is all zeros here, and let's say T and S, okay, small case, then the resulting ciphertext has the same IP header and TCP header information, and switch whatever this D was, the result has D XOR S, and whatever capital T was, the result has capital T XOR just little t. Why would adversary do that? Because in a application, the server, as you would expect, you know, if anybody's sort of halfway sane programs this, the server has to reply with acce or nax, depending on whether this parsed correctly. In particular, he decrypts the data, he decrypts the checksum, and he checks checksum, right? And if the checksum doesn't agree, then there is a message saying, the checksum failed, please resend, right? Because there was a communication error. So attacker can tell the difference between acce and nax, and so it basically it's even better. Sorry, I forgot. This particular application sent acce, and it didn't send an acce if something is wrong, right? Because you don't want to flood the counterparty, right? Like, that would be another side. I will send wrong stuff, and this guy would be flooded with nax. Okay, so I only get stuff back if I send stuff back if I got a correct formatted message. Okay, so this way, even if you encrypt, even if this went over the TCP, over encrypted connection, you would still tell the server sending something and server sending nothing. And what do you get from this? So the checksum is a linear operation. It is an operation that hold on, let me remove so I can see the slide. Okay. Checksum applied. The checksum actually applies to the header info and the data field. So it checks both the headers and the data. And now, if this shift created a valid response, then what the attacker knows is that the checksum function applied to the same header and a data XORed with the S shift that adversary chose is correct, which means that it is a checksum on this original data and the same header, XORed with this little t that adversary chose. By linearity of the checksum operation, this equation has, what are the unknowns here? Just D. I don't really care what this is. This is, the unknown is capital D. And header is predictable, right? The header is like IP addresses, counters, etc. And if there is some unpredictable stuff, then there's just like more, a few more fields that are unknown in this linear equation. So I can, by this linear, if I collect enough of these equations, I can solve for D. Okay. In fact, the negative also give me constraints. So I can even use these for to help solve D. Okay. So that's it. You don't need to know much, right? Checksums are often linear operations, right, for speed, right? Because like you checksum a big message by applying a linear transform. This way you can parse through, in a small circuitry blocks, right? You just rotate as you process blocks of the message. Okay, so okay, so all these attack patterns basically were examples of chosen ciphertext attack. Here, adversary chose a new ciphertext based on this one, and basically got some information from it. Here, likewise, he formed a ciphertext C prime based on some C, and by the way that this box reacted, it allowed him to compute the original plaintext. In general, what would these attacks look like? So now the adversary has both plaintext attack powers and chosen ciphertext attack powers. This is inclusive. So it's when we say indistinguishability, is he just gets a single ciphertext, right, on one of the two chosen messages. Chosen plaintext attack is that plus an extra ability to query the encryption box on multiple messages. CCA is all that plus an extra capability of decrypting, of getting access to decryption box and being able to decrypt any chosen ciphertext, except because then the security would be impossible, the challenge ciphertext, so to speak, right? The one ciphertext that without which the definition of security would be not clear what that even is. If intuitively, if the receiver decrypts everything for the adversary, then there is no security possible. Okay, so here is let me read so somebody asks, wouldn't the remote terminal attack also be able to actually take control of the remote server by figuring out the valid checksums of our possible keystrokes? Yes. So, right. Wait, by figuring out the valid checksums of. Well, the thing is here that in this attack, the attacker doesn't know anything about the key, right? It had nothing to do with the key in some way. It's just because the counter mode allowed me to take a ciphertext that encrypts some message under some key and modify it so that it encrypts under the same key some related message. And by the fact that I observe how the box behaves on this related message, this gives me some constraints on the original message. And so I'm learning information about the original message in here, actually figuring it out completely. And there is nothing known about the key. So yeah, Okay. So here is the box, the definition again. So far, this is the CPA security. Adversary has CPA access, chosen plaintext access. He specifies any message, gets back ciphertext. There is also this test query, like in the indistinguishability of encryption, the basic notion. You have some M0 star and 1 star, they have to be equal sized, and you get the ciphertext of either left or right. And now the new thing, CCA queries. Any ciphertext except for this one can be queried to the, and what you get back is the decryption. So this here is the encryption box. It's like as if you were asking the sender to encrypt stuff, so you can learn how chosen plaintext gets, and what are the encryptions of the plaintext you choose. And here is the decryptor box, and it's a chosen ciphertext. So you choose the ciphertext, and you get to see what that decrypts into. And the only constraint here is that you cannot just ask on decryption of this, because you would get MB star, and you know what M0 star and 1 star is, so you would output with B, right? There must be something unknown. I mean, the intuition is, if there is some message that you're attacking, and somehow you cannot force the decryption to just decrypt that for you, because if you could, then the security is clearly gone, right? But if, in spite of this one limitation, so you cannot get the decryption box to decrypt this message that you really care about, but you can get it to get you information about decryptions of any other ciphertext. And the encryption is CCA secure if that doesn't have. In other words, this bit is still just as uncorrelated with this bit, or there is like the standard negligible advantage in how this is close to that, in spite of this extra power of seeing decryptions of chosen ciphertext. So okay, so this is the standard thing that the experiment instantiated with this bit B, and the experiment output, which is B prime, when instantiated with bit B equal 1 versus bit B equals 0, these two are indistinguishably close, right? So that's this notion. So this is the same as you've already seen several times, right? Or many times. And all these examples, the port number and the terminal application, can be just captured as insecurity of counter mode against CCA's attack. And the insecurity is easy to see. Let the attacker choose to test messages. So this is the test query. He sees encryption of MB, so M0 or M1, depending on this bit. It's a counter mode encryption, so it has two blocks. Assume that these messages are a single block. It's a counter, so C0 is a counter, and the block number 1 is FK of counter XORed with MB. Yeah, that's a counter mode. And now, as your ciphertext, for a chosen ciphertext query, you choose a ciphertext which has the same 0 block, which means the same counter, and the block number 1 is the block number 1 here, XORed with some delta. That delta is exactly that delta which we used first to XOR port 80 with port 85, right? Or in the terminal application, take the payload and XOR it with, header checksum payload, XOR it so that you get the same header, and the payload and the checksum are XORed by some shifts little s little t that adversary knew. Yeah, and but this attacker can just choose delta any way he wants, And what he gets back is that because this is a encryption of message MB, but now shifted with this delta shift, right, which you XOR on top of it. And note, attacker can do it without knowing what's inside here. I mean, he knows that this is a counter mode, so he knows that this is a counter, and this is an FK of the counter XORed with some plaintext. He doesn't know, is it this one or this one? But he blindly XORs with a delta, and that is a ciphertext which is different, and its decryption is MB XOR delta. Since attacker chose delta, he takes his plaintext, he XORs delta out, he gets MB, he learns B, that's it, right? So it's a attack with advantage 1, right? As good as, it's a perfect attack. And this is how all these counterexamples, how all these attacks against the port, against the terminal, they worked exactly this way. And what was wrong with this was that it was the encryption was just CPA secure, not CCA secure. So this abstract ability of, if you can get a ciphertext to if you can have access to a decryption box that decrypted anything but C, then and gave you clear text to the output, then you would break counter mode, right? Counter mode is not secure against this form of attack, namely CCA attack. In these applications, it was not the case that adversary got the decryption in the clear. It only got it if the decryption satisfies some properties, right? Like if the port guessed was correct, or in the terminal, if some checksum applied to this message was correct. But it is some information. And these were examples where this information is actually tons of information and can be utilized in some computer system to great advantage, even though you don't get, like, the receiver doesn't just take ciphertext and outputs plain text. That never happens. I mean, that shouldn't, unless it's completely buggy, right? The receiver never should take the decrypted stuff and just sends it back in the clear. But what happens is that this clear text, some other process uses it. And these are examples where these other process essentially leads to a realistic attack. So we need encryption, which can kill all such possibilities in general and simply remain secure no matter what happens with plaintext that are generated in response to maliciously generated ciphertexts. Yes. So active attacker who sits on the wire and is active, we call that man in the middle. He can bombard the decryption box with arbitrary ciphertexts, and he can see what that box does based on them, no matter if the encryption is CCA secure. It should not help it should not give attacker any, except for negligible, advantage in attacking some real test ciphertexts. Okay. So now, of course, how can we assure this, right? Is the natural question. So we in the lecture and also in the book, we kind of have to take a detour, so to speak, because the way we're going to assure this is CC security is by message integrity mechanisms. So the reason why it will be impossible for a man-in-the-middle adversary who doesn't know the key to bombard this decryption with some ciphertext and observe anything from the plaintext is because the encryption would also contain like a signature on the message under the same key K. And since attacker doesn't know this signature, he cannot form valid ciphertext at all. So in other words, every ciphertext that attacker is capable of forming will be rejected by this box, because the box will use the key K not just to decrypt, but also to verify that this inside of this C prime stuff is sort of properly formed, properly signed, quote unquote, with key K. And so it will just always reject, no matter what adversary sends. Hence, sort of intuitively, it's an ability to access such a box will give adversary no advantage. So this is not the only mechanism to assure CCA security, but in a case of symmetric encryption, that's the dominant one. Not only that, it also serves other purpose, because in addition to assuring secrecy against active attackers, it will also assure other security properties that people want, which is reliability of the authenticity of communication, right? So far we talked about, as if the only thing that happens is that there is some two communicating parties who have a key, and all they want is to protect privacy of this traffic. But there is another thing that they want, which is that the adversary cannot inject and modify this traffic and, replace the encryptions of some M's with encryptions of M primes that are going to be swallowed by the decryption box and taken as if they came from this encryptor. Okay, so that's why we sort of, kill two birds with one stone here. Message integrity mechanisms will assure this message integrity, right, of communication, but also we will use them to solve this CCA attack, to create a CCA's attack secure encryption. Okay, so what is message integrity? So basically that data received by the receiver is the same data that was sent by a counterparty that holds the same key as you do. Okay, or that when you wrote stuff on the disk, right, and when you then read it, you can assure that what you read is the same things that you wrote, or based on the secrecy of a key that you use, right? So it's orthogonal, it's independent concern than confidentiality of these messages. And these two are, it's important to keep, separate these goals, even though they will be combined eventually, because you want all of this, you want confidentiality, you want integrity as well. But the mechanisms that assure confidentiality and the mechanisms that assure integrity, and then the way to combine them, are, must be kept separate. So as we have seen, encryption by itself, right, which is an intuitive. So before taking this class, you might have thought that when you encrypt, it's like some form of scrambling, so that it actually also protects integrity. Because if the message is scrambled completely by using an encryption, then how come that I can modify the ciphertext without knowing the key, and it will be descrambled, decrypted into something valid? If encryption is like this complete scrambling, then this is impossible. Well, encryption in some sense is not a complete scrambling, right? It accomplishes confidentiality, but we have just seen that it doesn't capture all intuitive properties that you or or a fifth grader would assume that an encryption has, that some perfect scrambling procedure has. And what the property of counter mode that allowed this taking a ciphertext and creating a new ciphertext that was somehow related, that's called malleability. And this is going to be an important word, because malleability will be a source of attacks, and preventing malleability was going to be a defense mechanism. But as in many things with cryptography, malleability is actually a double-edged sword. It could work to your advantage. The fact that you can take ciphertext and XOR it and modify it to something else, perhaps it can be used, I don't know, for some sort of remailer application where you just tell the router what the delta is, and he just applies it to ciphertext, and that means that these ciphers will flow to correct place, or they will be decrypted correctly. In data aggregation, malleability might be useful. You would take encryptions of different temperature measurements, and let's say if that was the case, that if you XOR all the ciphertext, you get a valid encryption of, okay, not XOR, add modulo some large number. You get an encryption of a sum of these measurements. Well, that would be beautiful. You would have a beautiful encryption aggregation scheme from that, right? With short bandwidth, you could take encrypted measurements from like some sort of sensors, and they would aggregate, and bandwidth is at price in these type of applications, and you would manage to keep it small. In a single ciphertext, you would convey encryption of all the of the sum, would translate to average, right? Okay. But in here you saw malleability as a in the service of an attacker, and the short story is that that captures these attacks on counter mode is that it is malleable. The counter mode is malleable. You can take counter mode encryption and without knowing the key and without really knowing the plaintext, and transform it into a new ciphertext, which under the same key is going to encrypt predictably a new message, which is related to the original one in ways that attacker knows. That's captured by this delta, okay? And all encryption modes we have seen are subject to this. Okay, so it's very easy to see in one-time pad. It's very easy to see in stream cipher because of its similarity. And counter mode is actually a form of a stream cipher too, right? You compute a PRG string and you pseudorandom string and you XOR the message. For CBC, it's a little more complex to see, not really, but I mean, it's just a slightly different way of attacking, but it's also malleable. Okay, so I guess this is just a repeat that this is what I was saying, that it's a malleable encryption. You don't know what's inside of the cipher. It's so here is XOR malleability of one-time pad. You encrypt by XORing with the key, and if I XOR with an added XOR the ciphertext with some delta, what it creates is an encryption under the same key of a related message, M prime, M XOR delta. And so this is the same This will apply to stream cipher, right? Just replace XORing with a key with replacing with XORing with GK, and it's also counter mode here. And CBC you check by yourself. So none of these modes have integrity, basically, right? Because I take a message that I see a ciphertext, and I can easily modify it to a ciphertext that contains, well, a message that is related. I can take all your, if I can predict what was where, I can change your messages in a way that benefits me. So here is what we want of a MAC. So a message integrity mechanism is going to be called a MAC. Sorry, I'm not sure where I have this. Maybe I had it on some previous slide, but I didn't notice. Message authentication code. It's a funny name. It's just a traditional name for these. It's called not a scheme, not an algorithm, not a protocol, a code. Message authentication code. It's a pair of algorithm, sign and verify. It's keyed algorithms, just like encryption. And it's here is the application scenario. You have a sender and a receiver, just like in encryption. And given some message M, the sender Alice is going to sign it using the signing part of the MAC. And the result is called a tag. It's not called signature because signature is reserved for public key counterpart of this. So these are called tags. So some people just call it MACs. I mean, they call the algorithm a MAC, and also this field, this data, they call it a MAC. So the verifier has a second. So this MAC has two algorithms: sign and verify. And the receiver uses the verifier algorithm using the same key and the message and the tag, and this just outputs yes or no, right? 0 or 1. And the correctness property is that no matter what key you chose, and there's also some key space and a message space of a MAC, just like a key space and a message space of encryption. So any key in a message in proper spaces, if the sender computes the proper tag, then the verifier will always accept it. Okay. Now, quick note, CRCs, so the collision resistant codes, right, are because they're unkeyed, they don't protect against that. It's a public operation. So the attacker can replace message M with M prime and tag with tag prime that is correctly computed on M prime, and the receiver will accept. CRCs are protecting random errors. So their security goal is that if there was a random error in communication and some bits were injected or flipped in here, then the CRC will be correct with negligible probability, okay, or very small probability. So these random errors will be detected, and so even better, corrected, right? But that's a second layer. But it doesn't protect against malicious errors, and that's what we are concerned here. So instead of random errors, you have an active attacker who tries to attack integrity protection. That attack is called forging. It's called forging the signatures, forging the tags. And security is called unforgeability. That is, that it's impossible to forge valid tags unless you know the key. So what is the attacker's power? It's something called chosen message attack. It looks syntactically very similar to chosen plaintext attack on encryption. Attacker chooses messages in the message space, and every message he chooses, he gets to see a tag. So this algorithm is going to compute the tag for him. This is the same as if, it's like a training part where he sees the signing algorithm compute tags on messages which perhaps are actually sent in the clear, or perhaps are otherwise predictable to the attacker. And after this learning phase, can attacker forge a valid tag on any message that is not in this among those that were already tagged, right? Because he can obviously resend, so he can take any message tag pair that was observed before and send that on the, so that of course will be accepted because just by correctness of the algorithm. So a MAC doesn't try to prevent what's it called? Replay attacks. That has to be protected on some other level. Okay, the application level, that's right, that keeps some counters or some buckets of received hashes of received messages. Yeah, but a MAC attacker succeeds if he produces any valid message tag pair on a message not in the set. And we will see later on reasons why you might want to strengthen this so that it counts as an attack, even if he creates a message tag pair that is not here, not one of these seen observed message tag pairs. How do they differ? Well, in this attack, even if M is equal to one of these, but a tag is not, if there is some other valid tag for the same message, an adversary finds it, then this is considered an attack on the strong notion, and it wouldn't be considered an attack on this notion. So if M is in the set, this notion just does not admit this as an attack, even if T was different from Ti. But this notion would. If M was, say, M1, but T was not T1, this would be considered an attack against a strong unforgeability. Okay, so here is this in a picture. Adversary is some key is chosen at random from the key space. Adversary chooses any message, gets a tag, chooses another message, gets a tag, etc. Then he outputs a forgery, claimed forgery, message and a tag. The experiment succeeds, so attacker wins if this is verified under this key, so it is a proper message tag pair, and the message was not one of these, right? Because that would be a trivial attack. And a MAC scheme, which is a pair of sign and verify, is secure if for all efficient algorithms here, the probability that this game is won is negligible, right? Where the probability goes over what? First of all, choice of the key that is chosen once and stays after that, right? Fixed, like in CPA security, like in CCA security, like in security of a PRF or a PRP, key chosen and then stays. And over possible randomness used in signatures, right? In fact, also over randomness that is possible in the verifier, although we will not see any example of the verifier that is randomized. So if you have such a MAC scheme, then you have a secure file system, because if you have a key on a USB, you create these MACs, attach them to files, And if the virus modifies this and somehow can create a pair, capital F, little t, that when you stick a USB later and you verify, it actually verifies, but it's new, then he breaks the MAC scheme, right? The MAC scheme must have been insecure, right? So this protects integrity of a file system, database, or what have you. And it also protects integrity of traffic. Yes, so let's look at an example of how to do it. So PRF actually implies a MAC. And for at first, it will be a MAC on a short message. So let's look at the PRF. Yes, so for example, any block cipher, right? The design principle is that it's a PRP, which means it's a PRF as well. It is a function on some key space, some argument space, and a resulting, and in the case of block cipher, X and Y are the same. Now we can define a MAC, which is a pair of S and V. The MAC is going to work on a message space that is the domain of the PRF. And to sign, the way tag is computed is simply, it's an output of a PRF on the message. To verify, the verifier, well, he has the same key, so he can recompute the PRF and just check against this tag. If there is a match, the verifier accepts. If there is no match, he rejects. Right? Now, it is why this is a PRF. Okay. So intuitively, why would you think this is a PRF, right? Well, sorry, a MAC. Well, PRF was supposed to look like a random function. So if this key K is chosen at random, then outputs of the PRF from the point of view of efficient attackers is like a random function outputs. So signatures are like a random function on the message. So therefore, signatures of one message are completely independent from signatures on another. So if you have seen F applies to a bunch of messages, this tells you no information about what F looks like on any new message. Therefore, you should not be able to predict these. So whatever new message you output as your forgery, and your probability of guessing the tag correctly is, well, the value of this PRF was supposed to be indistinguishable from a random function with this range. So it's 1 over the size of this range. So that's the only thing, that if the range is small, the tags are too short, right? You will be able to, just by guessing, you will win the game with the probability 1 over 2 to the 10, 1 in 1,000. And this translates into a formal proof. So the security of the advantage of an efficient attacker against this MAC in the MAC unforgeability game is bounded by an advantage of some very closely related attacker, reduction, against the PRF, plus just guessing an element, probability of guessing a proper tag in the range of the function. How would you prove this? So, you know, even if you take a DES, right, which has 64 bits of output, this is 2 to the minus 64. So that could suffice. How does this? So the proof is, okay, an attacker chooses messages and gets back tags, and right, and if so, suppose that we replace this function f, which is a PRF, right? So in a real construction, signature is an output of fk of the PRF with a random key k. But if this is a PRF, then fk should look like a random function. So let's just idealize this and think of f as a truly random function. In this case, attacker gets to see outputs of this little f, and the only way to win is to hit the output of f, to match the output of f on a message on which you haven't yet seen what the function evaluates to. That attack is 1 over the range size. And now you need to, so this gives you some basic intuition, right? And now you say, if this attack probability against the real function, the fk, right, instantiated with random key k, was epsilon away from this probability, then you could easily build a reduction which distinguishes the random function f from a PRF with exactly probability epsilon. Okay, and therefore, because such a reduction can be built, and it's rather simple, then so that reduction distinguishes random function from a PRF with the property epsilon. Therefore, by the assumption that the PRF is secure, you have some bound here on the best probable advantage that a polynomial time attacker of comparable resources can have against the PRF property of this PRF. That's the epsilon, and so this will get you the following bound. Okay. We can do this reduction on a piece of paper, because just for okay, like just completeness, and also make sure that everybody's on the same page. But this so far, this gives you that basically a PRF, like a block cipher, gives you an immediate MAC on short messages, as big as the plaintext block of the cipher, of the block cipher, right? 64 bits for DES, 128 bits for AES. Okay, that's a good place to start. We have some secure MAC already from a PRF. Now the obvious question is, like in the case of a PRG, you have something, or encryption, you have something that worked for short messages. Can you somehow build on this to have a secure PRF, secure MAC on messages of arbitrary length, right? These files in the file system example are not going to be single blocks, and communication are not single blocks, right? Like an IP packet is larger than 64 bits. So the next question is, how do you basically take a so-called small MAC that works on short messages, and convert it into a big MAC, a MAC that works on arbitrary of messages, however big you want. And small MAC is not only on small messages, there are fixed size messages, right? Like it has to be exactly 64 bits. Big MAC is not just on large messages, it's on large where the large is arbitrarily large. So I can mark single block messages, 2 block, 5 block, 10 block. I can use the same key without knowing how big the messages are, right? So in the file system example, like, my files are of arbitrary sizes. I don't have to somehow switch keys depending on how big the files are. I use the same key and the same software to encrypt each one. So, well, which is also the case for, that's at the beginning, it gave us a little trouble because, a PRG extends to fixed length, but we looked a little bit closer at PRGs and we saw that basically they have a tiny PRG inside and they can go for arbitrarily. The PRG doesn't need to know how much it needs to expand. Likewise, counter mode, CBC mode, OFB mode, they don't need to know how big the next message is. You can do it for arbitrarily sized messages. Same should be for MACs. So we will look at CBC MAC and HMAC. These are the main standards for how this extension to larger message sizes is done. And technically, the way both of them, they actually construct a PRF on a large domain. And so they are basically domain extenders for a PRF. If your block cipher is a PRF on short blocks, then these constructions, CBC MAC and HMAC, they construct a PRF that can be applied to not only large, but variably sized plain text. And on each of them, they compute some value, and that value is just a tag. So these constructions, work very similar using the same methodology of just like, well, just a PRF is a MAC. The only thing is that now we need a PRF on large blocks and of variably sized blocks. Okay, so I don't think that I should go there. In the remaining time, I can go over the reduction here, just so. Would anyone find this helpful if I showed this, if we just went over this argument of how the switch from a PRF to a random function translates into this bound? Okay. Good. So let's do that on the piece of paper, so that it can be visible. I will stop sharing at this point, and I will switch document to document camera, and no. Okay. Okay. So what was it that we wanted to prove? So the PRF, we had a PRF F from a key space message space and to some space y. Let me see if it's focused. Okay, yes. Okay, and we said that the MAC scheme is sign and verify, where sign using a key and a message is just FK of the message, and verify, given a key, message, and a tag, outputs yes, if and only if tag is simply matches a recomputed PRF, and this is a secure MAC with same key space as PRF, and the message space is the domain of the PRF. Okay, so that's the construction. Okay, and now the security experiment. So an attacker is faced with a challenger who picks a key from the key space. Okay, and the attacker sends some messages, mi, right, for I equal 1, 2, dot, 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 some Q queries, polynomially many, and each of them he sees a tag. But what is that tag? Well, it's just FK of the block, right? So the assumption is that each of these MIs are in the proper message space, right, which is the X. And then attacker sends an empty such that apparently, well, so we can assume that M is not in the space of these queried messages, right? Because otherwise that wouldn't be a valid attack. And let epsilon be, or let P be the probability that T is a correct forgery, right? Because so the advantage of A, the advantage in the MAC security of A is P. This is exactly its advantage, right? Where the probability went well, that the probability here is over randomness of A and randomness of key K, right? Because once key K is chosen, there is no more randomness used, except for adversary, possibly when he chooses these messages, and he chooses this message and this tag. So this is a randomized algorithm, possibly, right? Okay, so now let P prime be the probability that T is f of M. You know what? How do I say? Well, let me change this a little bit. So call this game 0. Okay, the starting game, the attack on the crypto system, and consider game 1, which is as above, but FK replaced by a random function little f that maps the same domain to the same range. In particular, let p prime be the probability that this is a correct attack on a function which is not fk but is little f. Okay, and also these outputs are computed using little f. So ti is f of mi for all I. Okay. So now let epsilon be the difference between p and p prime. Claim epsilon must be negligible if fk is a PRF. Okay, and specifically, there exists efficient reduction B, which uses this attack algorithm, and the advantage of against the PRF of the reduction B is exactly epsilon. Okay, so that's the reduction. Let's see how to do it. So the reduction B is has attacks a PRF. So it can send some messages and get back PRF values. Well, what messages should it send? Let's use this attacker A, who decides what messages it wants to see. So this B is going to choose these messages, and it gets back, and it accesses a box. Let's call it f star. So it outputs values like this, right? F star applied to mi, and let's call it ti. It's f star applied to mi. The reduction just sends these ti's to attacker, and it recurses, right? So this can go can recurse anytime. So attacker sends first m1, B just repeats it to f star, gets back the output, feeds it back to the attacker as the tag. Attacker asks for m2, and they repeat this. Then finally, attacker sends some m and a t. B at this point sends m to this box and gets back t star, which is f star applied to m. The reduction outputs 1 if t star is t, 0 otherwise. Okay, now observe. So what is I claim that advantage against the PRF property of this attacker B. So f star, it is let's consider a case of some secret bit B being 0. In this case, f star is equal to fk for random key k. If B is 1, then f star is function f random function, right? You have these two cases, and the advantage of B is the probability. Let's call this bit B prime. Probability that B prime is 1 given B is 1 minus the probability B prime is 1 given that B is 0, right? Okay, let's look what this probability. So what is the probability that B prime is 1 if B is 1? If B is 1, the F star is a random function. So this is the so it's a game 1. Attacker sends messages. What is the A's view in this process if F star is a random function? So A sends messages, and what he gets is a random function. The TIs are just a random function on MI. And when he sends MT, this bit is equal to 1, exactly with the probability that T is F star of M. That random function applied to M. So it is probability P prime. Right? Because B replicates the view of an attacker in this game. When this function is a random function, in this case, right? And this bit is 1, even only if there is an equality here. So if this was correct, if the T here was the correct one, okay? So this probability is B prime. Now look at the probability that B prime is 1 given that B is 0. So what now? In a B0, this box implements FK. It is like this, because in this case, these TIs, which are F star of MI, but F star is FK. So TI are FK of MI. That's exactly what happens here. Now, MT is output by attacker. And what happens with it? M is sent here, and what's T star is FK, because we are in this case, FK of M. So this equality holds if Fk of M, which is T star, is equal to T. Well, that's exactly this test. So this probability is P, which ends the proof, right? So therefore this is exactly the difference between P prime and P, and therefore this is equal to epsilon, right? And what this implies is that is this. Okay, so that was the reduction in the missing step, because the difference between the advantage of an attacker in the real game and in this idealized game where the real PRF is replaced by a random function, this distance is epsilon, which is the advantage, the maximum advantage of a similar attacker against a PRF. On the slide, what I had was an argument why P prime. So now on slide, we argued that P prime is upper bounded by simply guessing in the domain range, in the range of the function, right? Because this is just a random function output So if m is different, t is a random value. So I mean, the value of this function, of this random function on m, has nothing to do with the values on other arguments. So there is basically one in the range size probability of guessing it correctly, which is this part. And the two, so if this is something you establish, 1, and here is 2, and here is 3, if you take them together, then 1, 2, and 3 imply that P is bounded by 1 over epsilon 1 plus advantage against the PRF of B. Okay. When I photograph it, I understand that this is low granularity, so I'll just take a picture and attach it to the put it online, right? Like if it's hard to read, I'm not sure. Is it okay to read or no? Not really. Okay, yeah, I'll take a photograph of this. Okay. Any do you have questions on this? Well, I either lost some of you and maybe kind of burden others, or somebody says I need time to digest. Yeah. Okay. Yes, I will send a nicer picture of this thing. So I mean this picture, but the better resolution. It's not an uncommon. So it's like you know. What happens is somewhat simple, and at the same time it's hard to keep track of all these notation and right. So okay, just try to digest it indeed, and that is also in the book, because that's basically the proof of security of the basic PRF construction, right, on which everything builds. So it's the first one in the book as well. Okay. So I will end here, and is right, and go get a Big Mac, and as you enjoy the Big Mac, you know, try to understand the Big Mac constructions. All right, I will see everyone, and of course there's a homework out. Okay, take care. Oh, and there is no lecture on Wednesday. Sorry. So there is a holiday. I forgot what the holiday is about, but there is some holiday on Wednesday. So next time we'll see each other next week, or in office hours or so. Okay. All right. Take care, everyone. Bye.